Hello everyone, and welcome to this theory recording on capacitor and inductor circuits transient analysis. So in this video we're going to be looking at the source-free RL circuit. Again, a circuit that is a first order differential circuit would be characterized by having a first order differential equation. And as we indicated in the previous video, if you have a capacitor and inductor, in this case with the inductor, if you can express either the current or the voltages such that one of the expressions has a first order differential or is a first order differential expression, then you can regard the circuit as a first order differential circuit. How can we do this? We know that the voltage across the inductor, VL, is given by L di dt. Right. So what happens in the circuit first? What happens in this circuit? Why do we call it source free? We call it source free because a source is suddenly disconnected from the circuit, similar to the RC case. And once that source is disconnected, our interest is going to be the current response that's flowing through the inductor. So you'll remember that when dealing with the inductor, there were many factors that you would need to calculate the current flowing through the inductor. Right? VL is L di dt. The energy is a half Li squared. So typically when you think inductor, you must think current. And for us to then do a response, it would typically be the current response of the inductor. Now, how will we get the current response? So, similar to what we had done in the RC case, we have to do some KVL or KCL. In this case, we decide to do a KCL expression so that we can write the voltages in terms of currents. So, we will do a KCL where we will say VL plus VR is equals to 0. In terms of VL, we're going to say that's going to give us L di dt, and then in terms of the voltage over the resistor, that will just be plus I times R, where I is the current. That will give us 0. That's the expression that you see at this point. Right, from there on, you make di the subject of the formula. This gives you minus R over L dt. Integration of both sides and using Lin expansion will result in you having an expression that will be that the current IT gives you I0 e to the minus R over LT. Now, similar to the previous recording, we know that there will be a source that's connected such that you have an initial current, buildup before the disconnection. The disconnection happens at this point, and from that point onwards, the capacitor starts to discharge up until I at time t is equals to infinity is going to give you 0 amps at this point moving forward. What we're interested in is knowing what the rate of discharge will be. And as we indicated before, this must be dependent on the charging or discharging element. So in this case, it will be dependent on the inductor as well as the resistor that will be connected. So we then define again tau, which we said is the time that it takes for the signal to decay to 36.8% of its initial value. And in the case of an RL circuit, tau is given by L over R, where R is equals to RTH, and L is equals to the equivalent inductance. And then finally, your equation IT is going to be given by I0, the initial current, e to the minus t over tau. So the procedure with source-free RL circuits, first determine the initial conditions. So that will be the current flowing through the inductor at time t is equals to 0 negative, which is the same as the current flowing through the inductor at time t is equals to 0 positive. So as we indicated with the capacitor, the voltage does not change abruptly. The same principle follows with the current flowing through an inductor. So the current just before the change will equal to the current just after the change. Second, determine the time constant. We know that the time constant tau is equals to L over R. So we're going to need the inductance value, equivalent inductance, and the equivalent resistance value when t is greater than 0. And then finally, we determine the current response. We know that that current response, ILT, is going to give you I0, and this would be I0 e to the negative t over tau. Thank you for watching this video and enjoy the course.